Alright, so I believe this is part 5 of our video series of reactions of alkenes. We left off with the ozonolysis reaction with ozone. Here's the structure, or the just general reaction, where we'll ultimately split right down this carbon-carbon double bond, and we're going to get two of the oxygens inserted. You can think of it like that. We'll have a ketone, and depending on if there's hydrogens here, we'll have an aldehyde. Now, if this was an R group right here, we would have two ketones. The other oxygen, we can get an idea of what happens to that uh, by examining this a little. So here's our mechanism. We're going to have cascading of electrons again. So you can see this carbon-carbon double bond is reacting. We're breaking this pi bond going towards the positive charge. We're also having this negative charge being attracted to this carbon. When this pi bond is starting to break, this carbon here will become more and more partially positive, and that will attract the full negative charge on that oxygen. We'll get a five-membered ring transition state. This is super unstable. We have two side-by-side oxygen single bonds. So peroxide bonds are weak, so these two bonds are weak. This is going to rearrange itself into something that's still unstable but better than the side-by-side peroxides. So we can break these weak peroxide bonds. You can see the cascading of arrows. We're going to get this to split apart momentarily. We'll get a nice ketone out of it, and we'll get this oxygen-oxygen peroxide bond, but then also we'll have a ketone, or a carbonyl, I should say. This will have a positive charge on it and a negative, so this is overall neutral. This process happens very, very fast. The breakdown to the splitting right back to the formation of our different five-membered ring. So we're going to have this negative charge on the oxygen. This is called an alkoxide. Come in and attack the carbonyl. This will break this pi bond, send that up onto the carbon, and then this pi bond will be broken and sent onto the oxygen's positive charge. So the rearrangement here, we still have a peroxide bond, but now we don't have two. This is called an ozonide structure, which again is unstable. We're going to use dimethyl sulfide to break apart this interaction. For our course, we're not going to be looking at that mechanism, so you don't have to worry about that. And then we'll get two carbonyls, and it all depends upon what is attached here as our groups. If we have R groups, this would be a straight up ketone. If this one has R groups, it would still be a ketone. If we had a hydrogen, it would be an aldehyde. To try to cut back on the complexity of it, here's an example without any arrows. Have it labeled with two alkyl groups on the left, which are black R's, and an alkyl group and a hydrogen on the right in red. We'll react this with our ozone, and then we'll react with our dimethyl sulfide to break apart that ozonide and get our carbonyls. So you can see you're breaking right down the center, and whatever's attached to our alkene initially stays attached. So we just break this apart, split this part off, make it a carbonyl, split this part off, and make it a carbonyl. This on the left is going to be a ketone because we have two alkyl groups. On the right, we have one alkyl group, but we put a hydrogen in this example just to show that it won't always be two ketones. This would be an aldehyde. Here's two of our oxygens from the ozone. The other oxygen is going to oxidize the dimethyl sulfide to get this S double bond O. I'd like to end this discussion on alkenes by looking at three types of polymerizations. The first will be cationic, the second is radical, and the third is anionic. Let's begin with the cationic polymerization. We're going to need an alkene as well as a strong acid. In this case, this is sulfuric acid. So we can have sulfuric acid in water, which will form the hydronium. We can do the reaction with this hydronium. This will pull off a proton. We'll get water. We're going to add this proton. This is a Markovnikov type addition. So here's our carbon. This side we have two hydrogens. On the right we have two methyl groups. So on the left is less substituted, so that's where our hydrogen will add. Notice this went from H2C to H3C. Carbocation, we want to have that stabilized, so that adds to the more substituted side. So we have these two methyl groups donating in electron density onto that carbocation. Now we're going to get another equivalent of our alkene. This will act as a nucleophile on that carbocation. You can see we have our attachment. Here's our two methyl groups here, here. Here's this methyl group on the left, and we have this CH2. When this reacts, we're going to get the attachment from this carbon, which will leave an empty orbital and a carbocation right here. This will continue over and over and over as long as we have alkene present. This is a type of polymer, and this would be our monomer. The second type of polymerization is going to be a free radical type. We can utilize that weak oxygen-oxygen peroxide bond. If we heat this up just a little bit, this will homolytically cleave our oxygen-oxygen bond, and we'll get two radicals. Now we can add in an alkene, and this type of alkene is a unique reaction. This is called styrene. That's its common name, of course. This has two hydrogens on the carbon on the left. We have a hydrogen and a full benzene over here. So you can see this is our more substituted carbon and our less substituted carbon. We're going to take one of our radicals and undergo the radical reaction. Notice the half-headed arrows. The radical is going to go to the more substituted side. So here's our more substituted side, and practice resonance if you want to, and you need practice. This is highly resonance stabilized all throughout this aromatic ring, so it can go all the way around this ring. This will react with another equivalent of styrene, undergo another radical reaction, and continue over and over and over, and we get polystyrene. The last type of polymerization that we'll look at is going to be an anionic type. This will use an alkene, but instead of an acid, we're going to use a base. The base is going to act as a strong nucleophile with that full negative charge. We can react on the alkene carbon and attach the oxygen, break this pi bond. We can see the reaction moving forward here. We form an anion, which in turn can react with another alkene. I've just simplified this COOCH3, which is an ester to COOCH3. This is a cyano group, which I've abbreviated as CN. This will attach, break our pi bond, and we'll get this sequence, which will continue over and over and over. And this is an example with superglue. Uh, that's all of the material that I find necessary for you to see for the reactions of alkenes. Please practice these reactions. This is our last part. This is for Chapter 8. Thank you very much for your time and for watching these videos. Nice thing about these videos, you can pause and rewind and go forward and get lots of practice. I hope that you find great utility out of them. Thanks again.